Okay, so this week, thanks everyone for coming. We have John Rios from the University of Iowa going to chat. It sounds like a really interesting topic on price movements based on, I guess, networks of firms. This sounds interesting. So please,
Yep.
John, go ahead.
Thank you very much. And thank you again for organizing this. It's a really nice opportunity for us to meet with more students and to know what they are doing. All right, so welcome everyone. Today I'm presenting part of my dissertation. This is predicting stock price movement via interfirm networks. This is a project I've been working on with my advisor, Professor Kan Zhao, and with Professor Nick Street and Professor Jennifer Blackhurst here at the University of Iowa too. So today our world is more connected. The current situation with COVID is another demonstration of that. So this is a visualization of how the virus was spreading from different countries a couple of months ago. And companies are also that connected, right? So this interconnection of buyers and sellers is better modeled as a network than as a linear or hierarchical chain. And researchers have been using that to analyze, they have been using social network analysis to analyze supply networks. They have used these tools from social networks to analyze the main characteristics of supply networks. But also they have been using competition networks to analyze or to model disruption and disruption propagation in supply networks. But not only the companies are connected, but also their performance, and the performance can be measured by many metrics. When we are using stock price or stock return, researchers have been using news or log search to predict that as features, but also networks can be used here. And then they have been using like the amount of attention, for example, you use the investors pay to business partners to explain stock return, right? The idea behind there is that information is not necessarily flowing rapidly from one sector to another in the network. So you can, then it's not necessarily included in the price. So you can use that to show that they are related. Then we wanted to, based on this, have our research. So the idea is to go further, just business partners, and analyze the network itself. So we built a supply chain network and a competition network to predict or to see the association between stock price movements. So then we formulated these research questions. So the idea is based on, for example, some focal companies like Walmart in this case, or Costco. So we wanted to see how other companies are related to those. And the research question is, does the stock price movement of other companies in an interfirm network help to predict a focal firm's stock price movement? And then if yes, then what type of interfirm network is more predictive of the focal firm's stock price movement? So to answer those questions, we collected some data. We started with the companies identified in the top 50 by Gartner ranking in 2015, and used them as our seeds for a snowball approach. So the collection was based on a Mergent Online website. So we did some web scraping there and collected information about customers and different levels of suppliers in 2016. These seed companies are like supply chain leaders according to the ranking. So we filtering by keeping only those trading in the US so we can have return information. We ended with 27 seed companies. And then we built this supply chain network. This is like a super network connecting the supply chain network of each of the seeds. Then once we have the network, we also collected information about their competitions. And then we built the competition network, which is having exactly the same nodes, but stating another relationship. So in summary, we have a supply chain network connecting companies with suppliers and customers, but also using the same set of nodes, we have another network that is stating the competition relationship. Okay, so once we had our networks, this is just a snapshot of the companies that are included here, like the seed companies. And then once we have the networks, we collected also the stock price information. So we used the stock close price from CRISP and complemented that with Yahoo Finance. We kept the public companies trading in the US due to data availability. And then we were analyzing what we call the period 2, which is right after we collected the network. That would be 6 months or 127 trading days. And we also collected information about the companies 1 year before that in order to do some parameter estimation. All right, so this is a snapshot of the networks. So we have our supply chain network with 2,826 nodes and around 20,000 edges, an average degree of 14.66. These are the degree distribution of the networks. So the competition network is less connected. It has 11,000 edges. And we have like other metrics like the diameter or the size of the largest connected component. All right, so what is our predictive model? So the setting would be, we want to use performance of the neighbors to predict the future performance of our company. So we define a multi-class predictive model. We had the stock price movement from time t to time t plus 1, but predicting the movement by a tiny movement is challenging and not necessarily useful. So what we decided is to split into 3 classes. So we have going up, going down, or staying the same. And then we had to define a threshold about what means going up or going down. And for that, we went to our period 1 and collected the historical standard deviation of the returns of each company. And based on their own historical return, we define a threshold of 0.25 standard deviation. So it would mean that the company going up means that it's going above 0.25 standard deviations. So it's kind of a significant movement upward. In this case, we have almost evenly distribution of the 3 classes. It's around 1/3 of the observations in each of the classes. And we built one model for all the companies, and we used the 125 trading days in the prediction. The 105 companies we're analyzing would be our seed companies, but also we wanted to make it more robust, and we included all the companies in the Standard & Poor's 100. So we are predicting for all of them, for the 105 companies. It's a combination of the SP 100 and our seed companies. So let's see how we build the model. Now, what features are we using in the model? So we started with some baseline features that are coming from finance literature. So those are stock price at time t, stock return from time t -1 to time t, and the market return from time t -1 to time t. And then we complemented those baseline features with network-based features that we are formulating. So we first identify network neighborhoods. We have 4 definitions of network neighborhoods. And then we want to aggregate the stock price change of all the neighbors from time t -1 to time t. These are the features we are using there. So basically, for the focal companies, we're identifying neighbors, and then we're aggregating the stock price changes of these neighbors to predict a focal company. Now, what kind of neighbors we define? So we started with the basic one, just direct neighbors, so just direct suppliers and customers. So it has been shown in the literature that they work. So that's our first definition. So those would be for Walmart or for Costco. And then you can use the network and go further and include the 2 hub neighbors. That would be the tier 2 suppliers of your suppliers, and then also like tier 2 customers of the customers, and so on, for each of the focal companies. But in order to really use or take advantage of the structure of the network, we also identify some similar companies using network embeddings. So here we used a modification of deep walk. Deep walk is based on word to back, which is used for word embeddings. Have been like mentioned before in one of these presentations during the summer. And basically the idea here is to use some random walks around the network and use those walks as the context of one focal company. So that would be like the sentences in the paragraph. And then you are using that context to find a lower dimension representation of the node. Then each node in the network will have a representation that representation will include information about the network structure and who you are connected to. And then we are identifying who is similar to whom. So based on that, we identify the top most similar companies to define our embeddings, to define our neighborhood. And then the last definition is network community detection. So here we divided the network in different communities. Then the idea of these communities is that each node inside a community is more connected to other nodes in the community than to nodes that are outside the community. So they are more connected than to those outside. And then we are using those communities as the neighborhood. To make this fair, we are using the same number of similar companies in this definition of neighborhood than the network community we are defining. These communities, or this number of the size of these neighborhoods is much smaller than the two hub neighbors. So this will include a lot of neighbors that are not necessarily useful or relevant in the prediction. Okay, so then the challenge is how you aggregate them, right? One company can have like 10 neighbors and the other can have like 200. So how you aggregate all of them into a nice collection of features. So the idea here was to identify for each of the suppliers how different is, or how exceptional is the return on a particular day. For that, we define some bins using a similar definition of what we use for the target variable. So we have, so based on how far you are from zero, and far in this case is standardized by this, again, the standard deviation as in the target variable, you will be in one of these bins. So being around zero would mean that you are in the central bin, which is 6 here. And the further you are from zero, then the further you are from 6, right? The size of these bins is, again, 2 times 0.25 standard deviation. And in total, we had around 11 bins. Then the idea is to go over each of the neighbors and identify in which bin you are. Then you have a frequency of each bin, and those are going to be the features. So that's the way to aggregate all of the neighbors. Then you go to the next neighbor, or supplier in this case, and do the same, analyze what it is. So in that way, we have this data set. So we have the features are the baseline features identified from finance. Then we have 11 bins associated with the supply chain network. This is, again, including customers and suppliers, like all the neighbors, depending on which neighborhood definition you use. And we did the same for the competition network. So we have 11 more features about the competition network. And we have our price movement at time t+1 that we're predicting. And we have for company 1, we have 125 observations. Then we have for company 2, the same 125 observations, and so on, until company 105. Then the way we did the cross-validation here is what we call the leave one company out. In this case, let me move this here. In this case, we just hold out all the information about one company, and we train our model and validate our model. So train and tune our models in the remaining data and test it in here. Then we hold out the second company and so on. So then we are using information about the relationships of one company, of one focal company and neighbors. We're learning that relationship, and then we're testing how good it is in the prediction. All right, so these are the results we had. So we are using, so since we have 3 classes, we are using a macro AUC, or area under the ROC curve. The idea here is this metric will go from 0.5, which means random guess, to till 1. And we used the 4 different classifiers from different natures. So we use a lasso, which is a logistic regression, based on logistic regression. We have neural networks. We have KNN, or K nearest neighbors, and random forest, which is based on ensemble. We also are comparing our baseline features versus each of the neighborhood definitions we have. We can see that the network embeddings are doing a good job, and the network communities are also improving the prediction. So this shows that adding information to about the network into the prediction can improve, can help you to predict better. So other companies, it would mean that other companies in the network are associated with the return of the focal companies. You can this difference between each of the neighborhoods and just the baseline features are significant, statistically significant. But you can see that going further in the network is improving the prediction versus just using varied neighbors, which is what we had, or was showed before in previous literature. Also, this neighborhood, which the 2-hop neighbors, is including a lot of companies, and even more neighbors than these 2, and still is not better than the ones that are like smartly identifying which are the relevant neighbors here. So this is also like for the network community. So this is like a distribution of the percentage of peers that are 1 hop away, 2 hop away, 3 hop away, or 4 hop away, or more. So it's showing you that these neighborhood definitions are using information of neighbors, or identifying peers that are further in the network, right? And not only they are further, but they are relevant. We did some robustness check. For example, we identify if this improvement in the performance driven by just some kind of companies. Then to answer that question, we compare the improvement in performance, the performance improvement in the prediction improvement on different sector classifications. So we use NAICS here, the 2, 3, 4, 5, and 7. And also with the same with communities. Is one community doing all the good job? And no, we see that all of them are showing some improvement. So it means that it is the model in general which is learning here. So we also had an analysis of what happened if we exclude some of the type of peer. So it's just the are the customer relevant, or are the supplier relevant, or are the competitor relevant? And we see a decrease in the performance once we exclude each of them. And it is the same for the same in all cases, except for KNN with competitors. And the relationship with competitors is kind of particular because if the sector as a whole is going up or down, or it's better or worse, then all of them will move in one direction. So all of them move in the same direction, and the model have to learn that. But it also would mean that I'm getting a major share of the market, and then you are losing a share of the market. So in that way, the relationship is the opposite. So that's kind of noisy, and KNN is would be the performance of KNN would be hindered by that. Also, we are just reducing 11 features when we exclude the competitors. But here we're just excluding, we're changing the values of the features. So that would also be causing this difference. In general, we see that excluding suppliers is the one that is impacting this the most. But since we are doing this prediction for 3 classes, so we wanted to analyze what happened with the class -1, which is associated with risk. And then we see that also our model 4 and 5, the embeddings and communities are like doing a good job here. So that will give that can help managers to identify which is affecting me more. So going down is associated, so a decrease in the price would be associated with risk for that company. So that would be related to this part. And then going up would be associated with a better financial performance. And then also we see a good performance of the 2 models. All right, so to summarize and to wrap up here, so we built a large-scale multi-relational interframe network incorporating supply chain and competition relationships. We designed network-based features that reflect the performance of different types of network neighbors of a focal firm. And these network features can significantly improve the prediction of stock movement compared to baseline features. So managers can better understand the impact of business partners and enhance their decision making process. We are also now working on a second part of this. So the idea here is to define a new method to learn a neighbor information aggregation. So we had the bins, but what happens if we can create a model that can learn this relationship? The idea is to generate an end-to-end graph neural network approach for node classification over time. So the idea would be to create a neural network that is aggregating, learning how to aggregate the different neighbors of the company. We are using some techniques like graph sage and also attention mechanisms to learn which of the neighbors would be the most relevant one. Also, this method will, when you are learning how to aggregate the neighbors, it also will learn how to aggregate the neighbors of the neighbors. So that would be the idea. Also, the advantage of the next step would be like we are producing supervised network embedding. And it is supervised in the sense that we are using not only the network structure, but also network characteristics over time. And it will be learned by while we're predicting the stock price. So those will be associated with this particular task. And also we can in this kind of method, we can have a prediction including time series data further in the past with deep learning, and there would be something like LSTM or RNNs in general. So that would be it for today. I'm happy to take any question you have. And again, thank you for taking your lunch time to listen to my research, and I'm all yours. Hello?
Yeah, any questions for John? Well, what about maybe bankruptcy? Could you maybe use a model like this to
predict
bankruptcy, or maybe if or if maybe some of your competitors were going through hard times, maybe that improves your status? Or
Yeah, that's a good idea. So right now the prediction would be, so it's like day to day, right? You're predicting next day. So you have like some data that you can
Mm,
use to learn the model. So bankruptcy
yeah.
would be somehow like one observation. Uh, but you can do like some probability estimation, or like some survival analysis here, like complement this to like to see when you reach that point, or whether you don't reach it, right? But yeah, that's a good idea. Yeah, thank you. I'm actually taking note of that. Yeah.
Anybody else?
So, John, sorry, really quick here.
Right.
So, hey, how's it going?
Good, and you?
Your 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 prediction is just for one day, right?
Yep.
And so, could you maybe have that response variable be a quarter or a longer period of time and see?
Yeah, so we actually were analyzing this kind of situations. The thing is, like, when you do that, so in this case we are assuming that the supply chain is not changing, right? And it's not changing for that period of time. In the second part, we are assuming that it's not changing for even a longer period of time, which is not hard to assume, because these information is updated based on the report, the company report, like annual company report. So yeah, you can assume it's safe to assume that it will stay the same for 1-2 years, or maybe in some projects they've been using even longer. When you go to quarters, then you have less data. So that's why we are using daily return, because we have more information, and especially the models we are using now, the graph neural networks, are requiring a lot of data, and deep learning methods too. So if you use only quarters, then if you go with quarter, that would be less information.
Got it.
Yeah.
Thanks.
Actually, we are also in another project. We are complementing this with the board data. Um, we are trying to collect like supply chain information that is evolving through time. We are trying to collect that information from Bloomberg, but so far it's kind of manual to get that. And then, yeah, we are like, so the constraint is having the historical supply chain data in order to update the network, and can run this kind of models. But yeah, we're actually trying to do it, something like that. Yeah.
Anybody else? Any other questions? All right, John. Well, thanks so much for your presentation, and thanks everyone for tuning in. And we're in the home stretch of the summer. Only maybe four presentations left, something like that. So I'll see you all again next Wednesday. Thanks so much.
All right. Thank you. Bye.